Welcome to the deep dive.
Yeah,
Ever looked under the hood of a deep learning model? Felt like you're seeing something amazing, but, well, baffling.
definitely. If that's you, then today's exploration is probably right up your alley.
Yeah, we're diving into the math that really makes it all tick.
Yeah.
Matrix calculus. We're using the matrix calculus you need for deep learning by Terence Parr and Jeremy Howard as our guide.
Right. And for those of you who've maybe used libraries like, PyTorch or TensorFlow to train model.
Which is a lot of people nowadays.
Exactly.
Yeah.
Our goal today isn't just the how-to, the practical side. It's about getting a feel for the actual mathematical engine, that drives the learning. We're not aiming for like a PhD level understanding here. It's more about demystifying the specific bits of matrix calculus that are really, really key.
Totally. And matrix calculus, I mean, it sounds heavy, right? It can.
Yeah.
But like Parr and Howard point out, for deep learning, it's actually a pretty specific, manageable subset we need.
Think of it like understanding basic leverage. You don't need to be a structural engineer to, use a lever.
Good analogy.
Same idea here. Getting a basic grasp of this calculus gives you a much, much deeper insight into how deep learning actually works.
So fundamentally, training these models,
Yeah.
it's all about making them better predictors.
Yeah.
Right. Minimizing that loss function.
Precisely. The loss tells you how far off the model's guesses are, and to reduce that loss, we use optimization algorithms, things like gradient descent.
Okay.
And those rely heavily on calculating derivatives, basically, how much changing one thing affects another.
Right. Rates of change.
But in these big neural networks, the things aren't just single numbers. They're, collections vectors and matrices.
And that's the jump, isn't it? From scalar calculus to matrix calculus.
That's exactly where matrix calculus steps in. Yeah.
You might have seen basic calculus, like single variables, in maybe simpler machine learning things.
Yeah.
But with neural nets, all those layers, connections, you're suddenly dealing with really high dimensions. Matrix calculus gives us the tools to handle derivatives in that multidimensional space efficiently.
And the guides we have, Parr and Howard, they're excellent. Terence Parr, creator of ANTLR.
Oh yeah, the parser generator.
And Jeremy Howard from Fast.ai, known for making things accessible.
Right. Very practical focus.
Exactly. They bring this really practical view. This paper actually came out of their teaching experience at the University of San Francisco's Data Science Master's program. So it's grounded in, actually helping people understand.
Now, we should probably mention, we're kind of assuming you've got some basic familiarity with neural nets already, like you've seen or maybe done some training.
Yeah, that's a good point. This isn't really a neural networks 101.
No.
It's more for folks who've gotten their hands a bit dirty and are now thinking, okay, but how does the math work? What's really going on underneath?
And actually, Parr and Howard sort of suggest that having that practical experience first often makes the math click better.
Absolutely. It gives you context for the equations. And if things do get tricky as we talk, they mention the Fast.ai forums are a great place for questions.
Which is cool. Shows that commitment to accessibility.
Totally.
Something I liked in the paper was the reference section at the end. It summarizes the main rules and terms, like a little cheat sheet.
Yeah, super handy. Keep it nearby.
Okay, one last setup thing. Notation.
Yeah.
Yes, math notation. Unlike, say, the Fast.ai courses, which often use code to explain, this paper deliberately uses mathematical notation. Why is that important?
Well, it's not just to be academic. It's the language you'll actually see in research papers in more advanced textbooks.
Right, so understanding it is kind of a passport to that deeper literature.
Exactly. It's a key step.
Okay, so let's dig in. The big idea. To really get how deep learning models learn, especially the training part, we need matrix calculus.
Yeah.
It lets us figure out how changing whole sets of numbers vectors affects other sets of numbers.
Couldn't have said it better. That's vital for managing all those weights and biases inside the network.
Okay, take like a single neuron.
Yeah.
Its output is what, usually a weighted sum of inputs plus a bias, right?
Typically, yeah. Often followed by an activation function.
Right. And training means tweaking those weights, that bias, to get closer to the output we want.
Exactly. But scale that up. Networks can have millions, even billions of these parameters, the weights and biases.
Mind-boggling scale.
It is. So you need a systematic way, a mathematical way, to figure out how adjusting each tiny weight or bias affects the overall network accuracy.
And that's where gradients come in.
That's precisely where gradients come in. Matrix calculus gives us the tools to calculate them. Think of the gradient as like a multidimensional arrow. It points in the direction where the loss function increases the fastest. So naturally, we want to go in the opposite direction to minimize the loss.
Got it. So understanding gradients isn't just theory, it's like the map the model uses to find the best weights.
Exactly. It guides the optimization. Matrix calculus provides the language to even describe the landscape of possible weights and find the valleys, the minimum loss points.
And the paper explains the gradient is basically a collection, a vector containing all the individual partial derivatives.
That's right. The rate of change of the function with respect to each input variable, all bundled together.
And then what about when you have multiple outputs changing based on multiple inputs, like between layers in a network?
Good question. That's where the Jacobian matrix comes in. If the gradient is a vector of derivatives for a single output function,
Yeah.
the Jacobian is a matrix of derivatives for a function with multiple outputs. Each row corresponds to one output and each column to one input. It captures all those input-output sensitivities.
Okay, so gradient for single output, Jacobian for multiple outputs.
Yeah.
Makes sense.
And the paper does a nice job building this up. It starts with derivative rules you might know from basic calculus.
It's like the product rule, quotient rule.
Well, focusing more on extending them to vectors and matrices. How do derivatives work with element-wise operations, or multiplying by a scalar, or summing elements?
The building blocks.
Exactly, the fundamental operations you need before tackling the more complex stuff.
Now, here's something I found really interesting. The paper mentions that for many common vector operations in deep learning, like adding vectors or multiplying them element-wise, the Jacobian matrix turns out to be diagonal.
Ah, yes, that's a key observation.
So only non-zero values on the main diagonal. Does that simplify things somehow? Does it matter for optimization?
Oh, it definitely simplifies calculations. A diagonal Jacobian means each output element only depends directly on its corresponding input element, at least for that specific operation.
Ah, okay. No complex cross-dependencies at that stage?
Right. Think about an activation function like ReLU max, 0 input. You apply it element by element to a vector.
Right.
The derivative of the first output element only depends on the first input element. The second output only on the second input, and so on. That element-wise nature keeps showing up, making the calculus more manageable than it might seem.
That's actually quite reassuring. Okay, so we've got gradients, Jacobians, but you can't really talk about how things change through multiple steps, like in a network, without the chain rule.
Absolutely critical. The chain rule is the cornerstone.
And the paper walks through different versions.
Yeah, it builds it up nicely. Starts with the basic single variable one you probably learned first.
Diddex? Something like that.
Yeah, that's the one. Then it moves to a version accounting for indirect dependencies, and finally lands on the big one, the vector chain rule.
The workhorse, you called it.
It really is. It lets you calculate the derivative, or rather the Jacobian, of a function that's composed of other functions, where everything inputs, outputs, intermediate values can be vectors or matrices.
Okay, how does that work conceptually?
It elegantly breaks down the overall Jacobian into a product of the Jacobians of the individual component functions.
Ah, matrix multiplication of Jacobians.
Exactly, like analyzing an assembly line by looking at how each station transforms things and then multiplying those transformations together.
Okay, so bringing it back to the neuron. The paper applies these rules, especially the vector chain rule,
Yes.
to find the gradient of that neuron's activation, the max, 0, angst plus b thing. Specifically, the gradient with respect to the weights, W, and the bias B.
Correct, because those are the parameters we can actually change, the knobs we can turn.
And finding those gradients tells us how to adjust W and B to reduce the error.
Precisely. It tells you the direction and magnitude, how much a tiny change in a specific weight or the bias will affect the neuron's output, and ultimately the network's loss.
But how do we get from one neuron to the whole network's error? Does the paper cover that jump?
It bridges it. It shows calculating the gradient of a common loss function, like mean squared error, with respect to that single neuron's parameters.
Okay.
Then the magic happens through backpropagation. By repeatedly applying the chain rule, working backwards from the loss function through the network layers,
Layer by layer.
you can figure out the gradient of the overall loss with respect to every single weight and bias in the entire network.
So backpropagation is essentially the chain rule applied recursively across the network.
In essence, yes. The chain rule lets you compute how the final error signal propagates back, and the Jacobians at each layer tell you how sensitive that layer's outputs are to its inputs, allowing you to calculate the gradients for the weights in that layer.
Wow, okay. And that process, calculating all those gradients using matrix calculus and the chain rule, then using something like gradient descent to update the parameters. That's how the model learns.
That is fundamentally how it learns. That iterative process of forward pass, calculate loss, backward pass, backpropagation, to get gradients, update parameters, repeat.
So when you're watching your training loss go down in TensorBoard or whatever,
Yeah.
you're actually seeing the direct result of these matrix calculus computations guiding the model towards that minimum error state.
You've got it. That's the engine humming away.
Okay, so boiling it down,
Yeah.
a key takeaway seems to be that vector chain rule. XFGFGS looks simple, but powerful.
Incredibly powerful. It's the vector matrix version of the scalar chain rule and handles all that complexity of functions with multiple inputs and outputs. It really underpins how we train these deep networks.
And we saw how it applies to get the gradient for a neuron's activation, and then how that connects to getting the gradient of the loss, like SEWG. Understanding how those are derived feels pretty central to understanding optimization like SGD.
It absolutely is. But let me ask you, sometimes people wonder, well, can't we just approximate these gradients numerically? Why bother with the analytical form via matrix calculus?
That's a good point. I guess numerical gradients might be slow, or maybe less accurate for huge networks.
Both are true. Numerical approximations, while useful for maybe debugging or checking your analytical calculation,
Right, sanity checks.
they're generally much less computationally efficient, especially with millions of parameters, and they can be less precise. The analytical gradients from matrix calculus give you the exact direction of steepest descent, leading to faster, more stable training.
Plus, I imagine understanding the analytical form gives you more insight. Like, maybe it helps design better architectures or optimization tweaks.
Exactly. You understand the structure of the problem better.
So to really cement this, it's helpful to think about how these core ideas, matrix differentiation, the vector chain rule, apply even when things get more complex, like deeper networks, different activation functions, different loss functions.
Absolutely. The specific equations will change, they might get more involved, but the underlying principles, they remain the same. It's still about computing gradients via the chain rule.
And if you need a quick recap, that matrix calculus reference section in the Parr and Howard paper is the place to look.
Definitely keep that handy. A great summary of the rules and terms.
And if you want to go even deeper after this,
Well, the paper itself lists some good next steps. Checking out the Wikipedia page on matrix calculus is a solid start.
yeah.
Also looking at online lecture notes, lots of universities put theirs up. Or finding specific matrix calculus cheat sheets can be helpful. Just make sure you search for matrix calculus, not just vector calculus, to get the most relevant stuff for this context.
Good tip. Any specific books or articles?
Michael Nielsen's online book, Neural Networks and Deep Learning, is just excellent, a classic for understanding the fundamentals.
Hear that recommended a lot.
And if you're interested specifically in convolutional nets, CNNs, there's a great article called A Guide to Convolution Arithmetic for Deep Learning. Goes into the math behind convolutions.
Perfect. So ultimately, getting your head around this specific slice of matrix calculus, it seems like a pretty big unlock.
It really is. It might feel like a climb initially, but it massively improves your ability to read deep learning papers, to understand why certain methods work, to maybe even troubleshoot your models better.
Yeah, it moves you from just using the tools to actually understanding the mechanics behind the tools, the why and how.
Precisely.
So a final thought maybe for you listening. Consider how these principles, these gradients and chain rules, might play out in even more advanced architectures. Think about transformers or different kinds of recurrent networks or maybe complex loss functions used for specific tasks like object detection or translation. How does this core calculus adapt?
Yeah, that's a great place to let your mind wander. It's often surprising how these fundamental ideas scale and adapt. There's always more to explore.